Get interactive, unmute yourself and interrupt me anyway, and turn on your video. So we try to sort of model it a classroom without being there. So last time we were talking about uh, materials, different materials. And by the way, in announcement, I posted that I'll be posting these slides in the resource section. So what I'm presenting here, you'll find it in the resource section. So the slides, you don't have to take notes unless you want to, on the side, just append a few things, what we talked about. So you'll have these slides in the resource section. So last time we talked about materials, and when we think of materials, we are thinking of, in this context, electrical conductivity. So as we know, metals are highly conductive, insulators are not conductive or low conduction, and semiconductors are somewhere in the middle. They are not highly conductive, or they are not completely insulators. And in terms of classification, we said there are elements, right, that can be semiconductor, and those elements typically come from here, from column 4. And often we talk about silicon and germanium. Compounds, there are many, many different kinds of compounds that can be semiconductors. So these are simply examples. These are examples. And if you look in this particular example, we have a group 3 and a group 5 element combined to give us what is called a binary. Binary, of course, means 2. So you have gallium arsenide, 2 elements. So aluminum arsenide, aluminum phosphide, blah, blah, blah. We talked about this. And if you have 3 elements, aluminum, gallium arsenide, then it's a ternary. Now, what is missing here is there is something also called quaternary. And quaternary, an example would be 4 elements, as you can imagine. So you can have, say, for instance, if this is a ternary, so if I have indium, gallium, arsenide, phosphide, now this is a quaternary. This also is a semiconductor. Now, the reason why I wanted to throw this in is because this material system is very, very important. This indium gallium arsenide ternary and the quaternary indium gallium arsenide phosphide is very, very important in fiber optic communication. So when light travels down the fiber optic, you have to generate that light. And this is a semiconductor that can be used to generate that laser with that particular infrared light and detector as well. So these class of semiconductors are very important for fiber optic communication. But as do you know what is the wavelength of the light that is used in fiber optic communication? Long haul? Anybody? Okay, so homework. I'm going to ask you next time so that it becomes interactive. Homework. Long haul wavelength for, oops, I erased it, for optical communication. My hand is not steady with this. So I'm going to ask you next time, look up for long haul wavelength that is used for fiber optic communication. And you'll find, if you search Google, if you're looking for a detector or an emitter, you'll find some hits in Google that will mention these semiconductors. But I want you to look up what is wavelength that is for long haul communication. Let's see how many have joined in, participants. Okay, that's 61. Okay, that's nearly a few missing. All right, now, but for electronics, and as I mentioned, that these semiconductors can also be used for electronics, but they are very expensive. These semiconductors are very expensive. And they can be used for very high speed electronics. So gallium arsenide, for very high speed. Indium phosphide is another very high speed. Elemental semiconductors, particularly silicon, is very cheap, dime a dozen. That's just it's even cheaper than dime a dozen. But this is the mainstay, the bread and butter of electronics industry. So all your microprocessors, memories, all of that are built in silicon. Okay? Any questions up to this point? I think we went through this last time. No? Okay. All right. Now, last time we also talked about, so that is an electrical conductivity classification. When we look at the structure, and we are saying this, that the structure pretty much determines what its electrical properties and other properties would be, going to be. So when we look at the structure, we find in general materials, solid materials, and of course, I'm not going to talk in general now, I'm going to talk specifically in terms of silicon, can come in three states. The first is amorphous, right? So this is amorphous, where there is no ordering, there's no periodic order. It doesn't look like it's following any pattern. It's random atoms that are put together and sort of just, they bond with each other and then, it becomes a solid. Crystalline state of the same material is very ordered. You can see how they follow exactly the points where they are supposed to be, and they are very ordered, right? Exactly sort of the thing that you would see here. Polycrystalline is not quite completely crystalline. When we say crystalline, then all the atoms are. Here, you might see some regions that are sort of ordered. This looks like it is ordered. This looks like it is ordered, this group. And here, this group looks like it's ordered. But then when you go from here to here, the order breaks. When you go from here to here. So these are called grains. Wow, it's very slow. Okay, these are called grains. And the boundaries between them are called grain boundaries. So this whole region here, if you can sort of see, this whole grouping would be called a grain boundary. Obviously, as the name suggests, it's a boundary between two grains. And there can be a lot of issues with these grain boundaries. But this would be called polycrystalline state. Now, depending on how it is processed, you can have very small grains or very large grains. So, so it depends on all processing issues. So I suppose this is exactly what I mentioned here. Any questions on this slide?
None.
Okay, good. Now, our main interest is crystals. So amorphous and polycrystalline also have applications, but right now we are just going to be talking about crystals, meaning single crystals, crystalline state. And a few things that we need to know about crystalline state in general is that the first is that as if you have to give a name as to what is the arrangement that the atoms are following, it's called a lattice. So, this is, the atoms are located at lattice points. So this whole thing is a lattice. It's called a lattice. And since there is an order, it is repetitive, right? So it is repetitive. So in this particular, this is the three-dimensional view of a crystal. So if you look at a three-dimensional view of a crystal of this particular form, you would notice that I can pick out this particular box here, right? I can pick out this particular box, and that box, if I repeat, like in this case here, this is the repetition of this one. If you go, along this axis, If you go along this axis, then you find that this is a repetition. If you go below, then this is the repetition. And you can go left, right, all around. So if I pick this box and build with this box, identical box all around, I can get the crystal. I can generate the entire lattice. I can generate the entire crystal. So a unit within the lattice, which can be used to generate the whole crystal, when translated left, right, up, and down in 3 dimensions, that's called a unit cell. So if I were to say, what is a unit cell? I would say, yeah, this is a unit cell. Okay. Now, what is interesting about the definition of a unit cell is that you could say, look, this, oops, my hand is going all over the place. Let me erase this. If I could say, I'm going to be careful. This is a unit cell too, where there are 2 of these boxes. I combine them together, and if I translate up and down, I would get the crystal, and that is true. That is also a unit cell, right? Nothing stops you from picking 2 boxes together like that, and so that would also be a unit cell. Now, here we are showing this as a sort of a rectangle or a cube, but it doesn't have to be this way. You could argue very well that what if I chose, instead of going this way, I go diagonally across and I pick this as a unit cell? And the answer would be yes. You know, a box in that orientation, that would also be a unit cell, because now you can repeat this and you'll find that it'll get the same thing. Effectively saying, if you look at it from a 2-dimensional point of view, it doesn't matter whether your vector is like this, or like this, or like this, or like this. It doesn't matter, right? As long as you can repeat the whole pattern where the lattice and reach all the lattice points, you would have a unit cell. Okay, now, so that is unit cell.
I have a question.
Yeah, sure.
Can unit cells be made out of triangles?
As long as you can repeat the whole crystal with that same triangle. The unit, if you can use that unit and repeat left, right, up and down, and you get to all the lattice points, you can have a triangle as well. Okay. Now, mind you, I am emphasizing the name unit cell. Now, there is something called a primitive unit cell. Now, there is a distinction. So, primitive as in primitive. If I say this is a primitive unit cell, then what I mean is it's the smallest of all unit cells. Okay, so in two dimension, it would look like this. This is a unit cell, because if I repeat this pattern throughout, I get it, right? So this is a unit cell, fine, but it's non-primitive. But this is the smallest of all that I can make of unit cells that, when repeated, will give me the whole crystal. So primitive unit cell is the smallest of all unit cells. So there can be multiple unit cells, but there is only one primitive unit cell, which is the smallest, typically, right? Okay, so the distinction is primitive and just the. So here it's just a something that is a primitive unit cell is the smallest unit that can be repeated to form the lattice. Okay. Now, as in this particular picture, the sides may or may not be orthogonal. We showed that cube one, but it doesn't have to be a cube. It could be, it doesn't have to be orthogonal. So this is a generalized form of a primitive unit cell. Okay. Now, in your math classes and stuff, you would have seen how you represent vectors. So vectors are, if I were to sort of get to a particular point within the lattice, then I would use the Cartesian coordinate, and I would say that our vector is A, which is the basis vector here along the x-axis, B, which is along this axis, and C is along this axis. So A, B, and C. And these are the unit vectors. So this is, so if I say R is equal to 2A at 2B hat plus C, 1C hat, then essentially I'm going 2 units this way, 2 units this way, right? And then 1 unit up. So wherever that leads me to, if I join that vector, that's what I would have. So this is just a, your review of your coordinates in 3 dimension, right? Okay. All right. So that's nothing unusual here. Okay. Now, so the question is, remember where we are, what is that we are trying to do here? What we are saying is that a solid, when it is crystalline, it can take on certain lattice points. Now, what is done is, if you look at various materials, you find that they can be classified under various kinds of possibilities, okay, for how the atoms can arrange. And these possibilities are referred to as Bravais lattice. Bravais lattice, Bravais doesn't have any meaning, it's a name. It's a name of the scientist. Now, in this case, it was a crystallographer or somebody interested in crystals and understanding, and this goes back way back, 19th century. So, so there are 14 different classifications, 14 Bravais lattices, classifications of Bravais lattices. Okay, and what are those 14? Bravais lattice, different types. These are the names. You have triclinic. Now, A1, A2, A3 are essentially dimensions. Now, it doesn't show in this picture, but essentially, none of these sides are equal. Okay, it could be monoclinic, which might look like this. It could be orthorhombic. It could be like this. It could be tetragonal, like this. Trigonal, like that. Cubic, and hexagonal. So these are the groups. But when you count them, like this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there are 14 possibilities, right? Now within, say, cubic, let's pick cubic. Within cubic, you have 3 possibilities, right? So, and the others as well. So these are called Bravais lattices. So crystals in general can take on, some of these forms. I mean, each crystal has its it follows one particular form, but various materials, can take on various kinds of one of these crystal forms. So the question then arises, which one is silicon? Which is silicon? Among these, which form does silicon follow? So that is the next question that we will answer. It turns out that silicon follows a cubic lattice. And in cubic lattice, you have these, but then it is a specialized cubic lattice. It follows one of these plus some additional stuff. So let's go to the next slide and we will see, try to understand cubic first. Let's understand cubic and then we will see silicon in particular after that. So everybody is okay with this, that there are 14 Bravais lattices and that we are focusing on simply cubic because cubic is of interest because we will show that silicon follows a cubic lattice. Move to the next slide.
Yes.
Okay, thank you. All right, so let's take a look at the cubic, which comes from the Bravais lattice. Remember, we showed 3 of them. The first one is a simple cubic. Now, simple cubic essentially says that the atoms are located at the corners of a cube. Now, when we say it's a cube, meaning all the dimensions are the same, right? Cube has all the same dimensions, right? So, but the atoms are located on the corners of the cube. So that is simple cube. Then the second one is a body-centered cubic. Body-centered cubic is where the atoms are located not only on the corners of the cube, but also in the middle, right in the smack center of the cube. So there is an atom there, okay? So this is called body-centered cubic, which has an additional atom in the center of the cube. The third one is called face-centered cubic. Now, face-centered cubic has, again, 8 corners. These are the corners. These are the corners. And in addition to the corners, on the face of the cube, so let's say this is the face of the cube. This is one face of the cube. On the face of the cube, the center of the face of the cube, there is an atom. Okay. So it's very easy to imagine if you think of it as a cubical room, right? If you are in a room and there are 4 walls and a ceiling and a floor, that there are, right? How many faces would that room have? 6, right? There are 4 walls, and then you have a floor, and then you have a ceiling, right? So this could be the floor, this could be the ceiling. So you have 4 walls, and then on the center of the ceiling and center of the floor, you also have an atom. So this is called face-centered cubic. Okay, so it has additional atoms on each piece. Now, by knowing the locations of these atoms, we can find volume density. If you know the dimension of this cube, then we can find out, okay, what is the volume density? And some other properties as well, structural properties. And it turns out it also has an impact on electrical properties. Okay? Okay, next. Now, this is a view of the same thing. So here, as an example, it's a picture of a little different picture of a body-centered cubic. Unit cell contains, I'll come to this 2 atoms, why. So here you can see 8 corners. Now this is light because it's in the background. It's not, in view, it's in the back. And the body-centered meaning there is one in the middle, okay? Now, before I come to this picture, let me show you face-centered. So face-centered, again, these are the face atoms, on the face. So these are on the face. So that one. So the face atoms are this one, this one, this one, this one, this one, and this one. I don't know why it's drawing a straight line here. Okay. Okay. Now, in our problems, when you solve problems, this issue will come up. So this picture actually shows nicely what it is. Oftentimes in the problem, you will see the language of the problem would be considering each atom to be solid spheres, right? Touching each other, calculate, blah, blah, blah. So what it means is, if you think of this body-centered, right, then this body-centered atom here is not as small as it is shown in the cube. It's not like this. It's like this, like this. This is the one. So this is an atom, which is the body-centered middle one. And then you would notice that the corner atoms are chopped off, right? So here you see this is the corner atom, this is the corner atom, this is the corner atom. All of these are corner atoms. And the body-centered atom is right in the smack of it. So essentially, they're all touching each other for problem solving sake. So in this particular case, why is it shown like this? Because if this is my primitive unit cell, then this atom completely belongs to this primitive unit cell, right? The whole atom. But the corner atom is shared. Who is it shared with? It is shared with the one on top, the one on the side, you know. So if you think of this corner, how many cubes in a solid, in 3 dimension, when you put on the whole thing together, how many cubes would share that particular atom? Can anybody quickly guess?
8.
8. Yeah, exactly. So this corner is being shared by 8. So only 1/8 of that atom belongs to this particular cube. Does that make sense? So if I were to say how many atoms are in this particular primitive unit cell, in this unit cell, I would say there are 8 corners, and each corner atom is 1/8 contribution. Figure out what this line is. Do you see this line?
Yeah.
Yes.
I don't know why that line is coming. So corner atoms contribute 1/8, and there are 8 corners. So corner atoms contribute this much. And then there is one atom that is right in the smack in the middle, and that is the whole atom is part of the cube. So I have to add 1. Essentially, you would say there are 2 atoms. There are 2 atoms in that cube. So that's why it says unit cell contains 2 atoms. Now, when you look at this, can you tell me how many atoms are there? Of course, the answer is here. But what would you do in this case?
So the face ones are half an atom?
Face ones are half an atom. Exactly. So corner atoms are still the same. So 8 and 1/8. And then the face atom, there are 6 faces, and each contribute half. So that's 1 plus 3. So that's 4. That's how. So this also leads to what is called the packing density, how the atoms are packed. Okay. So these are 2 examples. Okay. And we go through this example right here. Simple cube has only 1 atom per unit cell. Actually, I would like to modify this to say primitive unit cell, because unit cell can be, general. So this is primitive unit cell. Body-centered has 2. Do the same thing, add that primitive, and 4 atoms. Okay. This is easily seen, right? Okay. Now, here's an example. As we said that we can do a few things. The number of atoms per unit cell is 2 for this must be body-centered. And we are interested in finding volume density. And the cube edge length is called the lattice constant, right? The cube, the cube edge length, so this dimension is 8. So, and it's called also the lattice constant. It's a very easy problem. It's given how much the cube edge length is, 5 angstroms, which is this. So the number of atoms is 2. The volume density is number of atoms per primitive unit cell. in this case, divided by volume of the unit cell. So A cubed is the volume of that cell. So you do this, and you get this. What I want you to remember is that roughly of the order of 10 to the 22 atoms per centimeter cube are per centimeter cube. Now, a centimeter is easy to visualize, right? You can think of a sugar cube that might be a centimeter by centimeter, and that will have of the size of a sugar cube. It depends on how much sugar you take, I suppose, but it has 10 to the 22. This is for a body center. But this order of magnitude of 10 to the 22, 10 to the 23 is something to keep in mind. We'll be seeing, we'll try to get intuitive feel of what's going on later, but try to keep that number in mind. So volume density is, in 1 centimeter cube, you have roughly 10 to the 22 to 10 to the 23. It's classwork, it's fairly straightforward. If it is face-centered, how many atoms do we have? We have 4. Lattice constant is 4.25. What is the answer? It's 4 divided by 4.25. So that answer should turn out to be this. Okay. So, all right.
Just a quick question
Yeah.
on that. Just a quick question on that one problem. You said for what do you call the lattice constant?
Yeah.
Is different for face centered.
No, this is this depends upon the material. So this is a different material might have different lattice constant. So this is just an example. So when we say body centered, consider this. It doesn't have to be this. It could be 6 angstroms, but it could still be body centered. So this is just an example that if it is 5 angstrom, then what would it be?
Right.
It depends on the atom size, right? So if you look in the periodic table, different atoms have different sizes. So lattice constants would be different for different materials. Does that answer the question?
Yeah, it makes total sense.
Okay. Now, what becomes relevant, it may not make sense right now as to why we are doing this, but in the context of what we'll end up doing later, is that we need to identify, directions and what are called planes. So within the crystal. So say, for instance, if we were to consider this particular plane, meaning if you're in a room and you look at one of the walls, that wall is a plane, right? It's 2-dimensional. So how would you notate, I suppose? How would you represent this mathematically or in numbers? And so these are called Miller indices. The method is used as called Miller indices. So the idea here is this particular shaded is called 100 plane, and this is 110 plane, and this is 111 plane. Now here's an algorithmic type of a way of doing it. Is the following. Next, Miller indices is what you do is find the intercept of the plane with the axis relative to the lattice constant. And we'll go back to the previous slide and do exactly that. So find where the intercepts are. Then once you have found the intercepts, find the inverse of that intercept. Okay, so you find intercept, take the inverse. Then use an appropriate multiplier to convert it to a whole number. Okay, and enclose the resulting numbers into a curvilinear bracket. So this is important. If it's in this bracket, then it is considered a plane. Okay, let's go back here. So the first step is what? Find where it intercepts, right? So this is A vector, B, this is your basis vector kind of a thing. So this is, think of it like this is the x-axis, y-axis, and z-axis. So where does it intercept? If this is my origin, where does it intercept?
At 1.
At 1, okay. So intercept is, I'm going to write it here. So this is intercepts at 1. this particular plane, where does it intercept y-axis or the B? This plane, think of this shaded area. Does it intercept anywhere?
No.
0.
We'll call it infinity. Parallel lines meet at infinity, right? So this is parallel to this. So it's running parallel to the y-axis. So this will intercept at infinity. Where does it intercept the z-axis?
Also infinity?
Infinity.
Infinity as well.
Yeah. Okay. Now, so we got the intercept. Now it says invert it. See, if I invert this, what would I get? 1 over 1, 1 over infinity, 1 over infinity. So what is that? 1, 0, 0. Okay. Now, the step after this was to convert this into a whole number. Well, it already is a whole number, right? I don't have to convert. Essentially, I would say multiply it by an integer so that it converts into a whole number. I'll have to multiply this by 1, right? So the next step is multiply it by 1. It's already a whole number. And put curvilinear brackets, this bracket. And that becomes the plane. So that's how you represent this plane. Do exactly the same thing very quickly on this one. Where does this particular blue plane intercept? X-axis? 1.
It intercepts at 1.
Yeah. Y-axis?
1.
1. Z-axis? Oh, no comments related. Z-axis?
Infinity.
Infinity. I invert 1 over 1 over infinity. What do I get? 1, 1, 0. Is this whole number already? The answer is yes. So this is a 1 plane. Okay? So this is how we represent planes. And we will see why these planes are important because electrical properties depend on it. So you go through this and you can figure out what the planes are. So this curved bracket, R representation of planes. Keep that in mind. Okay, so we already went through this. Then there is something called a direction. And the direction is very similar. It's very easy. But it is used with square brackets. So if I do Miller indices in square bracket, then I'm indicating a direction. So say for instance, this is 100 plane. But if I want, not interested in plane, I'm interested in direction, right? So if I just want to, so this is a direction, then how would I represent this? I would represent this as intercepts. It's going towards the x direction, of course, so that's 100. Okay. You'll notice one thing that you'll notice that 100 direction is perpendicular to 100 plane, and that is true for all the directions and planes. In this particular case, what is 110? So you go 1 along x-axis, 1 along the y-axis, right? And none on this side. So it goes along this face diagonal, and that is 100, and it is perpendicular to 110 plane. How about 111? Intercept at 1, intercept at 1, and intercept at 1. So there is a vector that you can use to join the body diagonal. It comes out of the body diagonal, and that will be perpendicular, orthogonal to 111. Okay. So the key thing to remember is that HKL in square brackets represents direction, and this kind of bracket represents a plane. Okay, any questions?
I'm sorry, could you repeat that one more time?
Which part?
You said we were talking about the square brackets and the parentheses.
Yeah, square brackets represent direction. So if I were to say, what is this? I don't know why it draws a line. Let me draw it here. If I do this and I say, what is this? Then you would say this is 100 direction. Okay, because of the brackets. If I said this, what is this? Then you would say this is 100 plane. And the difference in direction and plane is, of course, I'm referring to this direction, where when I say plane, I'm referring to this two-dimensional whole plane. Does that answer the question?
Yeah, that helps a lot. Thank you.
Okay. All right, here's a quick exercise. Crystal plane. If I want to figure out what plane is this, the first task is what? Where is the intercept? On the x-axis, what is the intercept?
3,
3. What is the intercept on y?
2,
2. Where
and
is the
z
intercept?
is
1.
1.
Okay, now I take the inverse. Okay, now earlier we didn't have to worry about the whole number, but now I have to convert this to whole number, right? What do I multiply this? The smallest multiplier to convert this to whole number. 6, right? If I multiply by 6,
Just kidding.
if I multiply by 6, what would I get here? 2, 3,
3, 6.
and what do I do in the end?
Well, you're just
Parentheses.
labeling it as a
Yeah.
plane.
I put the bracket. If I don't put the bracket, it's not complete. So I have to put that bracket. So multiply by 6, and then I get the whole number. So this plane is represented by this. Okay? Okay, here's the exercise. So here's the answer. Okay, a bunch of exercise for you guys to do. I'll also leave this for you to do. This is calculating, in the previous case, it was calculating the volume density. Now we are interested in surface density. So if I were to say, this is my plane, so it's a surface, it's not a volume. What is the density? So I have to figure out number of atoms per plane, how many atoms we have, and the area of the lattice plane. So this example already shows for in this case, the body centered. So you can see, look at this plane and you consider how much of it is included. So I'll leave this exercise for you to go through, and I'll do a little bit of thinking and come up with the answer. Now, this is the last slide I'm going to talk about before we close, because this is where I wanted to get to, is remember we were talking in general terms as to what is crystalline structure. So what is silicon? Which of these is silicon? Silicon is a specialized case of a face center, and it's called a diamond structure. The name of the structure is diamond. Which element makes up diamond, actual diamond?
Carbon.
Sorry? If you go to a store to buy diamond, which element is it? It's not silicon, right?
Carbon. Carbon.
Sorry? Carbon. Yeah, carbon. So carbon, the diamond follows with carbon exactly the same structure. And you can see why that would be the case. They come from the same periodic, same column in the periodic table. So silicon is the same structure as the carbon, and it's called a diamond structure, primarily because of that, I suppose. So what is a diamond structure? Diamond structure, this is incorrect. This is incorrect. It's actually face-centered. Now, I have posted this already in the resource, but you need to correct this. So basically, it is a face-centered. So I don't need to have. So basically, it is a face-centered cubic with. Wait, hang on. What is this? 4 of the corner. Okay, this is misleading. Let it. I'm using Dr. Kareem's slides. He said that's how. So, anyways, the way to look at it is the following: that it is face-centered. It's FCC lattice plus 4 additional atoms. Okay. Now, what is face-centered? Face-centered is corner atoms. So you can recognize all the corner atoms. Then you can recognize the face atoms. These are the face atoms, right? Those are the face atoms. Then in addition to those, there are 4 additional atoms inside the cube. Now, here, if you look at the picture, let me try to shade which are the 4 additional atoms that are inside this cube. There is one here. There is one here. There is one here. And there is one here. These are the 4 additional atoms. If you remove these 4 additional atoms, you'll find that this is a face-centered lattice. 8 corners and 6 faces. Okay? So silicon structure is a diamond structure, which is a face-centered plus 4 additional atoms. Okay? Now here, if you look at how the atoms bond, if you look at one of these inside atoms, you will find that it bonds to a face and corner, a face, and a face here as well. Okay? So that bonding of four dark lines that you see is a representation here. And it forms a tetrahedron. So it's a tetrahedral structure. So effectively here also you would note that a silicon has 4 nearest neighbors because it bonds to 4 nearest neighbors. How are we doing on time?
We're out of time, but
Yeah,
we're way over.
Yeah, okay. So this is a good place to stop. We'll probably finish chapter 1 next time. So, complete your reading and we will meet again on Monday. Any questions so far?
No.
Okay. Is this any feedback? Any quick feedback? People who have to go, they can go. People who want to hang around and give me feedback as to how this is going.
actually, I just have a question about how you can, well, because so far we've only done an example